You ever wonder how we captured this image, the first ever image of a black hole? The answer is radio astronomy. Radio telescopes collect long wavelength signals, but this comes with an inherent challenge, the diffraction limit. Since this limit depends on wavelength, longer wavelengths blur the image, making it harder to see fine detail. You can think of it as the smallest area a telescope can see clearly, like this. To improve the resolution, astronomers must build larger satellite dishes or observe at shorter wavelengths. But let me take a step back. If shorter wavelengths lowers the diffraction limit, why go through the trouble of making large and expensive dishes? Well, shorter wavelengths like X-rays are blocked by our atmosphere and gases orbiting the black hole. Even with the advantages of radio astronomy, you wouldn't be able to resolve M87, the black hole in this image. That's because when you calculate its angle in our sky, it's only 0.04 milliarc seconds. That's a million times smaller than a degree. When you use this angle in radio wavelengths to calculate the aperture size you need, you get an aperture. So what do? Build a telescope the size of the Earth? Not quite. Instead, we use very long baseline interferometry, or VLBI. VLB works by having many radio telescopes located all across the world, observing the same object to mimic the effect of having one Earth-sized satellite dish. With these tools and a bit of timing adjustments due to Earth's rotation, we've shown how the Event Horizon team created this image. Although this image was monumental for being the first to confirm a prediction made 80 years ago, VLBI and radio astronomy go far beyond that. They let us create 3D maps of our own galaxy, test dark matter theories, and keep the timing standards that our GPS and phones still use. In other words, this technique doesn't just capture images of the unseeable. It reveals the universe's best kept secrets.